The next speaker will be Professor Georg Feulner of the Potsdam Institute for Climate Impact, and the title of his talk will be, again, the faint young sun paradox.
Okay, thank you very much for the kind introduction, also for the invitation. It's a pleasure to be here, although I must admit that I feel a little bit like an exotic species because I'm not a cosmologist. I started out as a cosmologist, actually. I did a Master of Science project on structure formation in the universe, did my PhD actually on the evolution of galaxies, and only later on became a climate scientist. So this is like a journey back in time for me in a way. My presentation today is also a journey back in time, back to the early Earth, and talking about the faint young sun paradox you've heard a little bit about already. So that's the outline of my presentation. I will briefly introduce the faint young sun paradox again. I will give you a brief overview of earlier research on the subject, and then I will give you an update on what has been happening recently in climate science towards three-dimensional model results for the climate, for the faint young sun paradox and the climate on early Earth. And then I will talk about implications or possible implications for cosmology. So what's that faint young sun paradox? Again, it has to do with this beautiful celestial object, and of course the question is, why was the young sun so faint? And this is basic physics, basically, relating to the structure of the sun, which we understand actually fairly well. So we have this huge plasma ball, mostly consisting of hydrogen and helium. It has a hot core, it has a radiative zone, it has a convective zone on the top, and then it has a complex set of atmospheric layers, of which the photosphere is the one which we usually observe in visible light. Looking at the basic physics, the governing equations for a star like the sun, it's basically a mass conservation law, it's an hydrostatic equilibrium equation. We have conservation of energy with the energy production rate, and we have energy transport through those layers of the sun, plus equation of state, nuclear energy production laws, and so on, and some boundary conditions. So it's fairly standard physics, as a matter of fact, and you can run models for such a star, like the sun. The important thing is that, as all of you will know, the sun produces its energy by nuclear fusion of hydrogen to helium. The most important is the pp chain, the proton-proton chain. The details can be fairly complicated, but what you do in the end is you fuse 4 hydrogen nuclei to 1 helium nucleus and get a lot of energy from that, as a matter of fact. Now, because over time you accumulate helium in the core and you basically destroy hydrogen nuclei, so to speak, the particle number in the core will decrease. This will decrease the pressure, and to keep in hydrostatic equilibrium, the core will have to shrink. But this, in turn, increases the nuclear fusion rate of hydrogen to helium, so the sun has to increase in luminosity. You've seen a version of this diagram already. What you see here is the solar luminosity in units of the days, luminosity as a function of time, going back the 4.6 billion years the sun has been living so far. What you see here is basically the solid line is one particular solar evolution model. They're all fairly similar, and a famous approximation formula which has been widely used over the last decades, which agrees actually very well with those detailed solar evolution models over most of the solar life. And indeed, if you go to early Earth, say 4 billion years back in time, you will see that the sun was considerably fainter than today, about 25% fainter than it is today. Now, this is interesting for the Earth's climate system, because if you look at the climate energy budget today, you will see that actually almost all of the energy the climate system receives comes from the sun. So for the present-day climate system, it's 99.98%. And you can forget all the other terms like geothermal heat, waste heat from industrial production, or tidal friction. They're just negligible. The same is basically also true on early Earth. You don't have any industrial waste heat, of course. Geothermal heat flux is a bit higher, but even if you scale that up by a factor of 3 or so, you still end up with the sun being the dominant energy source of the climate system. So these results were actually fairly well known by astrophysicists early on, say in the late 50s or early 60s, and actually they started to speculate, whether this could have had any effects on the Earth. Schwarzschild, for example, wrote in 1957, "Can this change in brightness of the sun have had some geophysical or geological consequences that might be detectable?" It's an interesting notion at a time when geophysicists were not at all aware of that, probably, I guess. And Ringwood wrote at the early 60s, "Other factors being equal, the surface of the Earth during the period of its birth 4.5 billion years ago and 3 billion years ago would have passed through an intense ice age." So he is making really that leap from the faint young sun to an intensely glaciated Earth. And I will show you in a minute that with this restriction, other factors being equal, that's actually a very precise statement. And the problem which the Earth system faces if you reduce solar luminosity or reduce temperature is actually due to a positive feedback effect, one of the dominant positive feedback effects in the climate system, and that's the ice albedo feedback. Just to illustrate this, these are satellite images from the September minimum of the Arctic sea ice comparing 1984 to 2012. So what you see is global warming in action, basically. But this is just an illustration for a general effect we have in the climate system. That if you have a colder climate, then of course you have more ice, you have a higher albedo, that's the reflectivity of the Earth's surface, so the surface gets brighter. So even more solar radiation is reflected back into space and it gets even colder. It's a classical positive feedback loop. We just observed the reverse actually for warming the Arctic. But if you cool down the planet, this is what will kick in eventually. And this can lead actually to a fully glaciated Earth, or Snowball Earth as we call it in climate science. So what you see here basically is a stability diagram. That's the latitude of the ice line. So the latitude where the boundary between open ocean and ice would be as a function of solar luminosity. So up here you would have an ice-free Earth. Down here you would have actually a fully ice-covered Earth, a snowball state. So we are here today. If we heat enough, which we probably won't manage, or hopefully won't manage, then we will jump into the ice-free branch. But if we cool down, or say reduce the solar luminosity, then most models say that if you reduce the solar luminosity by something like 10% or so, then you will then end up in the fully glaciated snowball state. So if you reduce, like on early Earth, solar luminosity by, 20 or even 25%, then you should be really in this ice-covered branch. Yet, as we've heard, there is ample evidence for the existence of liquid water throughout the early history of the Earth. There's sedimentary rock throughout this early period from many, many places and many times during the Archean. The Archean rock record is sparse, but still we have a lot of sedimentary rock. I've got a piece of it, 3.8 billion year rock sitting on my desk, as a matter of fact. So there was liquid water, because without liquid water you wouldn't get any sedimentary layers. We have no evidence for global glaciations. For later periods of time we have scratch marks and all other sorts of evidence for glaciations. We don't have such a thing for the Archean, that time period on early Earth. And as we've also heard, that's exactly the time when actually life originated on our planet and, as far as we know, prospered. So we can assume that there was liquid water on the surface of the Earth, and no global glaciation, no Snowball Earth state. I should mention that there are even a few people who think that not only there weren't any glaciations, but that the early Earth was actually extremely hot, with temperatures not in the range of present-day ocean temperatures as shown here, but even above that, reaching maybe 340 degrees or so. I should mention that this is sort of a minority position, but it's not completely ruled out as far as we know. So we could have even had a very hot early Earth back then. So that's the faint young sun paradox. It was first pointed out actually already by Donedal in 1965, but as it is so often the case in science, it needs one of those high-level, high-impact journal publications to make it widely known. In this case, it's a famous Sagan and Mullen paper in Science, 1972, which you see here, and is actually a description of the comparative analysis of the atmospheric evolution of Mars and Earth, pointing out that you would need something to compensate for the faint young sun to explain what happened on early Earth, but in particular also on early Mars, where the problem is actually more severe than that. So that's basically what we call the faint young sun paradox. Early research on the subject. If you face this paradox, then what could really solve that? So there could be something wrong with basic physics. There could be time-varying fundamental constants, or there could be a cosmological effect, right? As we'll point out later on, we cannot exclude this at the moment. This is entirely possible. There could be problems with our solar evolution models. This has been discussed quite widely when the amount of neutrinos we received on Earth did not match what the solar evolution models predicted, but that, as you all know, turned out to be a problem with the fundamental model of particle physics rather than our solar evolution models, which are now fairly well calibrated also, with all sorts of solar observations. So I don't really think there's something fundamentally wrong with our solar evolution models. We could have had the effect that the young sun was actually more massive than we thought. We could have had a higher mass loss rate, for example, through the solar wind. This is widely discussed, but from observations of solar analogs of stars similar to the sun, it's actually, you can't get enough mass loss to really make the faint young sun paradox go away, I should say. There could be a geometric effect. The Sun-Earth distance is increasing with time, either due to a cosmological effect or some dynamical phenomena. There have been studies trying to sort of kick the Earth at an appropriate moment of time so that it changes the radius of its orbit. But it's all, you can make this sort of work, but you need a lot of, assumptions and very special scenarios to make this work. So I really don't believe that any dynamical effect is at work where the Sun-Earth distance is steadily increasing with time. So most people have actually focused on all possible explanations which involve the variables affecting the Earth's energy budget. That's clearly the concentration of greenhouse gases or the amount of clouds. If you have less clouds, then less radiation is reflected back into space, for example. Or you could have a lower surface albedo or a darker surface, or a combination of all those very, very messy factors. Just to illustrate that, that's a snapshot of the Earth's global energy budget today. We receive an average of something like 340 watts per square meter on solar radiation. About a third of that is reflected back into space, both by clouds and by the surface. About 2/3 gets through and is absorbed by the atmosphere, but mostly actually by the surface. That surface is heated up, re-radiates in the infrared. Most of that actually escapes into space, but due to the presence of greenhouse gases, some is actually absorbed in the atmosphere, and there's some back radiation in the infrared warming the atmosphere. So if you want to compensate the faint young sun, you can either decrease the reflected part by having less clouds or somehow darker clouds or a darker surface. Or you can basically adjust the amount of greenhouse gases if you believe that the solar influx is what the solar evolution models predict. Early explanations have focused on the greenhouse effect already. That's actually what Sagan and Mullen explored in their 1972 paper, and they thought that we had a strongly reducing atmosphere back then. That was actually indicated or sort of suggested by two lines of argument. The one is that early models for the formation of the Earth suggested something like a very slow accretion process. And if the material on Earth accretes slowly, you have time to oxidize it, and you end up with a very reducing atmosphere in turn. And also there's the famous Miller-Urey experiment where if you if you pump electrical discharges in a strongly reducing atmosphere, then you get all sorts of amino acids and or other prebiotic molecules. So that's then what they say in the paper. What you see here is basically the time evolution for the case of the Earth and the surface temperature. And you see that going back in time, surface temperatures gets colder due to solar evolution. But if you take an atmosphere which contains ammonia and methane and water vapor and CO2 and other gases, you get a pretty strong warming, and you can reach actually mild temperatures with such an atmosphere. This solution got completely unfashionable over the years, and that's because it turned out that the required amounts of ammonia would have to get is actually destroyed by the UV radiation from the sun within a decade, and there's not enough outgassing actually to compensate for that. It's also soluble, so it is rained out of the atmosphere, which is always bad for a greenhouse gas. And also later models for this formation suggest that the accretion process was actually fairly fast, so we wouldn't really end up with a strongly reducing atmosphere. So then, of course, the natural culprit becomes CO2, carbon dioxide, and this is an attractive solution because, as we now think, carbon dioxide is part of a negative feedback cycle stabilizing the climate on very long time scales. Anyway, that's that weathering cycle I will explain to you in a minute. So basically, in long-term equilibrium, the amount of CO2 outgassed from volcanic eruptions is actually balanced by the amount chemically bound by the weathering of rocks and then transported to rivers and to the sediments in the ocean. And that's a negative feedback cycle because if you increase, for example, the amount of CO2 in the atmosphere, it gets warmer, you get more rain, and the rain is a little bit more acid, so the weathering rate increases. So more CO2 is chemically bound, transported with rivers to the oceans and put into the sediments in the oceans. And it's more than, on average, on the long-term average, is actually emitted by volcanic eruptions. So you reduce the amount of CO2 in the atmosphere. And of course, also works the other way around. It's a very nice negative feedback cycle which stabilizes the climate on the long run. So that's one argument in favor of CO2. And then there's certainly enough carbon in the Earth system. It is stable, it is not destroyed CO2 by any UV radiation from the sun, and it's also not really soluble in water, so it's not really completely rained out. A slight disadvantage is you need a lot of it. And the favorite models analyzing the faint young sun paradox for decades were just models for one atmospheric column where you basically compute the radiative transfer of solar radiation and of infrared radiation in one atmospheric column, as I said. And those indicate that you need something like 1,000 times present-day levels to reach the same temperature we have today, 288 K or 15 degrees centigrade. So that's quite a lot of CO2. It's not technically excluded, but it is a lot. One should keep this in mind. Are there any empirical estimates for CO2 at that time? What you see here are a few empirical estimates we have for the carbon dioxide partial pressure, which is shown here as a function of time or alternatively solar luminosity. So we go back here to the beginning of that Archean period, 3.8 to 2.5 billion years ago, having 75% the solar luminosity of today and going to something like 20% theta sun at the end of the Archean. And those 1D model runs I was referring to, you can see here. This is what those models would predict in terms of the carbon dioxide partial pressure you need to reach the freezing point of water and to reach today's temperatures. And those are the empirical estimates we're having. So estimating ancient CO2 concentrations is an art in itself. You can do that from the geochemistry of ancient soils and whatever. You will also notice that there are huge error bars involved. You will also notice that some upper limits actually contradict some lower limits, but that's, you know, sort of the situation we have to live with in paleoclimatology all the time. But, you know, most of them actually are, you know, for the late Archean, early Proterozoic, we're probably around 10 to the -2 bars. Pre-industrial CO2 concentration you can see down here. So now you've got a problem, because depending on whether you say a freezing point of water globally is enough to prevent a snowball Earth, or you need more, you don't really know whether you know you can make it with CO2 alone, given those results from the radiative convective models. Methane could help. That's an estimate of methane concentrations in the atmosphere, which are much smaller, and then the CO2 concentrations over time. So recently we can measure this, of course, and we can also trace this back from ice cores over the last million years or so, and then we're basically left on our own and have to estimate from the fluxes we assume. Abiotic sources are very small on early Earth, but, you know, once you get life, we get methanogenic archaea, and so we get a sizable methane flux probably. You see the estimate here in green from the early biosphere. So methane could help, at least for the later Archean, until it is destroyed by oxygen, basically. Problem with methane is you can't go to very much methane, to very high methane concentrations, because once you go beyond a certain mixing ratio, which is usually measured to be 0.1 in laboratory experiments, then you form something like a haze layer, organic haze, which then scatters solar radiation back into space, which is not really what you want to have if you want to warm the early Earth. But as I said, we don't really know what the methane concentrations were back then. We are dealt with it. We have to deal with estimates from the biological production. But this is, you know, the sort of atmospheric evolution in terms of carbon dioxide, methane, oxygen, and so on we could be looking at, with fairly high carbon dioxide concentrations. Then methane comes at some point. Carbon dioxide is decreasing, both because of increased weathering, because the continents are growing, but also because the volcanic flux decreases. Methane helps here in the late Archean, and later on we go basically down the road. So it's all perfectly plausible, but we don't have much empirical constraints, or many empirical constraints on that. There's a fundamental problem with what I've told you until now, and those are the model results, basically. We need the models to tell us how much CO2 is required to offset the faint young sun. And those are 1D models, as I said, they model one atmospheric column. What they completely neglect is any spatial effects, and what they actually neglect is the ice albedo feedback effect, which is a bit bizarre, because it's the one effect you have to overcome to compensate for the faint young sun, basically. And those models have been used for decades, studying the faint young sun paradox. And we also don't have any explicit description of ocean dynamics, heat transport processes, sea ice dynamics, and so on, which is also important for the ice cover. So that's one of the reasons why in my 2012 review of the faint young sun paradox, I've strongly argued that the time is ripe to run, you know, 3D numerical simulations of the early Earth climate system to finally, you know, find out how much CO2 we actually need, and whether this is consistent with, you know, the estimates, the geochemical estimates for the ancient CO2 concentration. And this is what I will be talking about next. These are a brief report on the recent three-dimensional climate model results and how they compare to both the empirical estimates and the earlier 1D model results. So this is basically the situation we had earlier. This is an iteration of one of the diagrams you've seen already. That's a CO2 partial pressure in bar as a function of the solar luminosity changing with time. And those are the two 1D model results for a global temperature of 273 K and 288 K I've shown you earlier. And those are the more reliable, I should say, empirical estimates for the ancient CO2 concentration, shown in gray. So again, this is a radiative convective model without any ice albedo feedback. So what we've done, we've tried to run the first 3D models for the Archean climate, for the climate on the early Earth, getting the boundary conditions as precisely as possible. So we've reduced the solar luminosity by 25%, for example. We chose randomly scattered small continental fragments because that's what our geophysics colleagues tell us, that the continents on early Earth were fairly small. And we, try different of those random configurations to sort out whether, or to check whether this makes any difference or not, and so on. So we ran a lot of model simulations to check that. And those are actually the first 3D modeling results for the climate on early Earth from my group, as I said. And we've done that for 3 time sizes, basically at the beginning of the Archean, somewhere in the middle, and towards the end. And what you see in blue is the coldest, not fully glaciated state. So anything with a lower CO2 concentration will be in a Snowball Earth state. So that's sort of the critical state you have to reach to counteract the faint young sun. And also some results which go toward the present day temperature of 288 K or so. And what you see immediately that they are actually above the 1D model results, which in itself is not completely surprising because, as I said, the 1D model results neglect the ice albedo feedback, and once you cool down the climate, actually this feedback produces a lot of ice and a lot of cooling, and you have to overcome this with a higher CO2 concentration than actually estimated by the 1D models. This is all very fine, and then there came a lot of modeling results from other groups, which looked completely different to our results. Actually, they had 280 K at considerably lower CO2 partial pressures, and not fully glaciated states, cold states, also at lower temperatures, and all was actually pretty comparable to the old 1D results. Right? They looked fairly in the same ballpark. But I have to say, in science, the majority isn't always right. And I guess much of that difference is actually due to a climate model design. And I have to go a bit into detail here so that you understand that. So what we used an ocean general circulation model, meaning we simulate the full 3D hydrodynamics of the ocean, including the ocean heat transport, which is important for the ice line. We have sea ice dynamics, meaning that sea ice doesn't only, don't have freezing of seawater when it's cold, but our ice gets also pushed around by the winds and by the ocean currents, and this is extremely important, close to the critical state, as I will explain in a minute. But we have a simplified atmosphere model. So to do those long simulations and ensemble simulations, we need a simplified atmosphere model, which is not so nice, which is the point in our study, which is probably the weakest. What about the others? They are much better on the atmospheric side. They have atmospheric general circulation models, so they have the fully 3D dynamics of the atmosphere. But then it gets a bit difficult. So what they use, they don't have any ocean dynamics, but they only simulate the uppermost layer of the ocean. And in terms of heat transport, they can't really simulate that. They prescribe the present day heat transport. So they basically take the heat transport from the present day system and put it into the early Earth system, which is sort of questionable at least. And they don't have sea ice dynamics, and this is really dramatic, as I will show in a minute, because we know that models without sea ice dynamics are artificially stable, because you get a nice tidy ice line, but you don't get any ice pushed by the winds and ocean currents towards the equator, which could destabilize your climate system. And this has actually been shown in a number of model studies, and this is just one example. What you see here is a comparison of different model runs now for the climate state 635 million years ago, so it's a much more recent state where we had the last Snowball Earth glaciations. And what you see here is basically the sea ice fraction if you concentrate on the right-hand scale. So this is the fully glaciated Snowball Earth state as a function of atmospheric CO2 concentration. What you see in blue is basically a standard run of the model. So it's a full ocean dynamics plus atmosphere dynamics model. If you reduce the CO2 concentration, at some point you fall into the snowball state, and you fall in the snowball state somewhere, above 10 to the 2 ppm of CO2 concentration. If you use the same model and switch off sea ice dynamics, that's what you get, right? That's the red line. So at much, much lower CO2 concentrations, your model is stable and stable and stable and stable. And finally, this also will fall into a snowball state, but it's actually, it's 2 orders of magnitude. It's a factor of 100 in the CO2 concentration, which is the difference between a model with and without sea ice dynamics. So neglecting sea ice dynamics is deadly if you want to study glaciation thresholds. And just to point out, if I would apply a factor of 100 in this plot, then probably all those results would move up considerably. Yeah. The problem is we really do have to do those model simulations with fully coupled atmosphere dynamics plus ocean dynamics model, and no one has done that so far. And until that, that dispute is not resolved. I think that we will end up here. And that means that actually we need even higher CO2 concentrations than predicted by the 1D models. And that also means that for much of the Archean, for later Archean, where we have geochemical estimates, CO2 alone is insufficient to counteract the faint young sun. Something else will have to help, be it cosmology or methane or something like that. And that brings me to the last part of my presentation, and these are potential implications for cosmology, and that's that bit you're most interested in, I guess. What I want to say about that is that, as I pointed out earlier, a solution of the faint young sun paradox in terms of any changes to fundamental physics or in terms of cosmological effects is by no means excluded by anything we know about the Earth system, right? We don't have any hard empirical estimates which say there is no other way to solve the faint young sun paradox. So at the moment, this is entirely possible, I guess. As I said, the problem is both from the modeling side and from the empirical constraints, we just don't know, right? The Earth is an extremely messy system. It's probably one of the messiest systems you can possibly study. And going back in time, the information gets very, very sparse. So we're still not there to say that there is something from our data which would say we need something like a solution in terms of fundamental constants or cosmology. Nevertheless, I should like to point out that there's a wide range of, I would say, less exotic explanations available. And some of them, like higher CO2 concentrations, they are entirely plausible. There's nothing in our knowledge about the early Earth system which would tell us, there cannot be a solution in terms of higher greenhouse gas effect, in terms of CO2 or methane, and so on. But as I said, more data and better model results might change that picture. But at the moment, there is no, I should say that a cosmological solution is not excluded, but there is no strong argument from the Earth science side that you actually need one, right? So that's would probably be my summary for all of you. Coming to my conclusions, what I've shown you is the faint luminosity of the young sun is a fairly robust prediction, actually, of solar evolution models. So there are very few people doubting that there is something wrong with those. Now, the point has been made early on that this decrease in solar luminosity, a decrease of 20 to 25%, should have turned Earth into a snowball. And now comes the important bit, if all other parameters had remained unchanged, right? We know that there's geological evidence for liquid water on Earth, and this, contradiction between those two has been termed the faint young sun paradox. But it's important to note that it's only a paradox if you keep all the other parameters unchanged, right? And there's actually no reason to believe that, CO2 concentration or anything else in the Earth system hadn't changed over time. It's actually fairly plausible in terms of CO2 concentrations that we had more CO2 in the past. As I just said, solutions in terms of fundamental physics, including cosmology, are not excluded at the moment from the data and the model simulations we have. But you know, the faint Young-Sun paradox is not a strong argument in favor of any changes to fundamental physics or cosmology. It's just too messy, to be quite honest. So the most likely solution from the Earth scientists' point of view is still a stronger greenhouse effect on early Earth, probably by CO2 very early on, and by a combination of CO2 and methane later on, once we had the biology to support methane production, biological methane production. And this actually can, as far as we know now from all the constraints we have, actually solve the faint Young-Sun paradox. And finally, I've told you a little bit about 3D climate model experiments for the early Earth. But still, as I've showed you, there's still some debate about the amounts of CO2 required, because the problem has been tackled with 3D models finally, but with two very different classes of 3D models, and there are, you know, reasons to believe that those structural differences between those model classes actually produce the discrepancy we observe in the model results. So there's still some work to do for us. And with this, I would like to thank you for your attention, and of course happy to answer any questions you might have.
Okay, we have a lot of time for questions.
Excuse me, you described several possible explanations. What are your preferred? What do you think yourself?
What I think what we have is that combination I was speaking about. Well, let's take this plot. I don't think that CO2 in the later Archean is sufficient to solve the faint Young-Sun paradox. I mean, those estimates have huge error bars, but I still believe that it will turn out in this ballpark, and that the climate solutions. Yes, that's CO2 greenhouse. For the early Archean, I think it's CO2 alone probably, because there's no reason to believe that CO2 couldn't have been higher. And actually 1D models for the evolution of the carbon cycle say it should have been higher early on. So I think it's CO2 early on and CO2 plus methane in the later Archean. But there could be contributing factors. So clouds may play a role. Those are usually, you know, following modern present-day clouds in our climate models. They could be changed, and I think this could play a minor role. And so it might also be a combination of different factors, but the majority of the factors probably greenhouse gases. So at the moment, we don't have any reason to believe that this would not work. We can't constrain it very well, but we also can't say it won't work.
But you must remember that all the planets, it says from central body, it's already for all the planets in the solar system.
Well, if there is a migration outward,
also moves away from the sun.
If there is a migration outward, this will certainly help because of the distance. Works in this direction.
The moon was closer to us.
Yes.
And, it would have probably led to stronger tidal forcing and stronger volcanic activity. Potentially this would be a fairly strong effect, a non-linear effect even, in increasing the CO2 concentration, as well as actually just heating.
Exactly. So there is higher geothermal heat flux already on the early Earth, but you know, tidal friction and tidal heating could amplify that. Still not enough to completely offset the problem, as I said. But in terms of the CO2 flux, for example, this could be an important factor producing the high CO2 concentrations we see on early Earth. And we have a second effect actually, which is making it a bit harder, and this is the rotation rate of the Earth. Because the Moon was closer, the Earth rotated faster as far as we can reconstruct, and this also has implications for atmospheric and ocean dynamics, which make it actually a bit harder to counteract the faint Young-Sun in our model simulations.
Yes.
Do high volcanic activity in the early Earth have influenced the climate in some way?
Yes, by CO2 emissions, for example. So they emit carbon dioxide, and this warms the planet. They also emit, you know, each volcanic eruption also produces sulfur aerosols, In the modern climate system, those end up in the, those end up in the high atmosphere, which was not the case on early Earth because we don't have this atmospheric layering because the ozone layer wasn't there because we had no oxygen. But the primary effect then is actually warming the planet by CO2 emissions.
Because nowadays a big volcanic eruption make the climate cooler.
Yes.
So you say that at the early Earth it would be the opposite, just the warming.
So in the long run, of course, those volcanic eruptions accumulate CO2. The CO2 flux today is very, very small, but it could have been higher on early Earth, or presumably was higher because of the higher geothermal heat flux, or also because of tidal effects by the closer moon. And then basically for longer time scales, that warming effect due to greenhouse gases like CO2 actually is the dominant effect.
Thank you.
Professor Coleman.
Would the energy deposition by bombardment, by the brace of from the formation of the solar system, would that be significant?
It probably was in the very early days, so even before the Archean, where we still were in this accretion phase, that could have really contributed. There is some debate how that bombardment actually tailed out into the Archean. There's even some debate whether the slate-heavy bombardment just before the Archean is an artifact or not. So that could, in the very early days, also have deposited some energy to melt it. But probably, you know, you wouldn't get a continuous melting, I should say, right? You would still get episodic events of melting, but what we are looking for actually a solution which you know keeps the Earth above the snowball threshold continuously.
And a related question, not related, another question. If I understand correctly, in the T-Tauri phase of the Sun, the luminosity was higher, no? Than today.
The T-Tauri
and the radius was larger. So how it's one thing to say, well, we have a nuclear, we have main sequence stars and do the exploration, but or do you really know how the transition from T-Tauri to main sequence occurs?
Well, that's something you would have to ask on stellar astronomy, but that phase was earlier, right? And then the climatic effects we're talking about here.
This is probably for the 31st million
years, yeah.
And then at this stage, the sun was probably 100 times brighter. This is a very short phase.
And much earlier than the effects we're looking at here.
The question is, you have a sharp cutoff, or it's a gradual transition to the main sequence?
Even if it's gradual, it happened much earlier than the effects we're looking at.
That depends on the rate of change.
I guess.
Yeah. Saying that it's much earlier means it's like it's exponential decrease, something like that.
Well, we're talking at least 500 million years, so you know, even if it tails out, it should be over by that time. But there could be effects from higher solar activity in general, which are not entirely taken into account in model simulation. Some models do that; they increase the UV flux and so on from the young sun for that stage to see if there are any effects. But climatically, those are usually not particularly.
How much time does it take to clear out, say, the envelope of the T-Tauri? I mean,
again, are there any stellar astronomers who can answer this question? I'm not the expert there.
I think it's about the same order. Within 30 million, everything it's essentially clear.
Yeah.
Yeah, but it may still engulf like a cocoon the inner planets, no? The mass ejected.
Of course, there are still some debris falling nowadays, but essentially the strong accretion was shorter than the so-called Kelvin-Helmholtz time scale, which, as I said, is of the order of 30 million.
Okay, thank you.
Okay, I'll let us thank the speaker again.